This is, ideally speaking, gas laws, all right? The combined gas law, which you guys seem to get, P1V1 over T1 equals P2V2 over T2, is wonderful if you want to find out some information about a gas if you know a before and after situation. However, there are times where we want to know about a gas right now. We don't care about before, we don't care about after, we want to know what that gas is going to look like given a specific set of situations, specific set of circumstances. Okay. The ideal gas law works nicely under ideal conditions. Remember, we're dealing with the kinetic molecular theory here. So there were some assumptions that were made in the kinetic molecular theory that doesn't make all gases work the way the ideal gas law says it should. Slide here. What we mean by ideally is that gases act ideally when they're at low pressures or when they're at relatively high temperatures. When you let gas molecules get closer together, if you're not at low pressures, if you're at high pressures where you're pushing those gas molecules closer and closer together, or if you're at cool temperatures where those gas molecules wind up getting closer and closer together, you're starting to get away from the assumptions that the kinetic molecular theory made. Okay, one of those assumptions you might remember is that the volume of the gas particles, the actual molecules, should not be significant. But if you start getting them closer and closer and closer together, the volume of the empty space gets less and less and less. Suddenly, the size of the actual molecule, the volume of the molecule, starts becoming significant. And that's where the ideal gas law breaks down. And it doesn't work well. Okay, so if you get really cold or low pressures. The other assumption that was made in the KMT was, oh no, that's not the bullet about the other assumption. We'll edit that part out in a second. All right. At high temperatures, gas molecules are moving so fast they experience neither repulsive or attractive forces. Okay, so that was part of it. Is that the other thing the KMT makes an assumption about is that there are repulsive and attractive forces going on between the molecules. When you get them really, 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 really close together, the attractive and repulsive forces start adding up. And again, it's causing problems where the equation for the ideal gas law doesn't work out the way we want it to. You wind up getting ridiculous. You wind up getting answers that seem reasonable, but in reality are not reasonable. Does that make sense? Here, the majority of what I'm going to be testing you guys is on this idea, okay? This is the ideal gas law. Nerd. Don't mispronounce it. Okay, the Pivnert equation, PV equals nRT, is the equation that talks, that is called the ideal gas law. It tells you, given one set of conditions, what a gas is going to do. What its volume is going to be, what its pressure is going to be, what its number of moles is going to be, or what its temperature is going to be based on what you're trying to solve for. You guys might notice that there's a new letter in there that you don't recognize. R. It's Pirate Day. Right? Okay. The reason why R exists. Put your pens down for a second. Thank you. Pay attention to what I'm saying for just a second here. People wanted to figure out if there was a way to do this. If there was a way. Oh, excuse me. Gotta have the N, not the R. Okay. So people were trying to figure out whether they could figure out if a system could be predicted. So they took the pressure and the volume and they multiplied them by each other and they found out that, oh, this should not be equal to. This should be approximately equal to. Okay. They found out that the product of the pressure and volume was approximately equal to the number of moles times the temperature. It wasn't perfect because rarely is anything that we ever study perfect. Okay. They found out it was really, really, really gosh darn close. So what they did was they put a constant in there that would always be there called R. And they made up an artificial value for that is the ratio of the difference. Okay, so that it would always be equal. So they came up with this value R. And R is a value for you guys of 0.08206 liters times atmospheres per mole Kelvin. R is really, really complicated, right? Okay, the units on it are complicated simply because they want those units to cancel out the other units in the equation. You know, with P1V1 equals N1 P1V1 over T1 equals P2V2 over T2. You always have two pressures, so the pressure units would cancel each other. You have two volumes, so the volume units would cancel each other. If you're looking for temperature, you have one temperature unit, so the other temperature unit doesn't get canceled, so you're left with temperature units. Okay, because I don't have two pressures, two volumes, two numbers of moles, and two temperatures, we have to do it this way. Okay, the R is actually going to be the canceler. Question. Really, mathematically speaking, you could just throw numbers in and it'd be fine. What this one value, this constant, does for us is it forces us always to have our units in volume for liters. We have to have our pressures in atmospheres. We have to have our number of moles in number of moles. So if they give it to you in grams, you have to do a conversion. And you have to have all your temperatures in Kelvin. All right, check this out, guys. Problem number 1. Sulfur hexafluoride is a colorless, odorless, very unreactive gas that happens to be really cool. All right. It says here to calculate the pressure in atmospheres exerted by 1.82 moles of gas in a steel vessel of volume 5,430 milliliters at 69.5 degrees Celsius.